Okay, good morning. So I'm going to finish up this chapter on main memory and go into a few of the assignments. So this is where we left off last week. We were talking about these shared pages, and actually before then we were talking about page tables. So page table allows you to implement shared memory pretty easily at the level of pages. So instead of saying from this address to that address, that range, you actually can just do a mapping of a page and saying, well, that's your granularity. So you will share in multiples of these pages. So if you have less, well, you get the entire page. But if you have more, you use multiple pages. So that way, the bookkeeping is a lot easier. And all you have to do is for each address space to have its page table mapping to the same physical page. In fact, they could even take different logical pages and map to the same physical page. And that's often done in the case of executables and shared data as well. Okay. Now, there's issues with page tables, especially as the processors become more capable in addressing larger address spaces. So the last decade, we've seen shift from 32-bit addresses to 64-bit. And 64-bit is likely to be enough for a while, but then we don't want to keep saying, well, 64 is all you ever need, because Bill Gates got dinged for saying 640K is what everybody will need for a long time. Well, that turned out to be wrong. But I mean, 64-bit is huge. And even if it's going to run out, still, I mean, this is huge. And what's an implication of huge address spaces is that you have a lot more page table entries. So your page tables are going to be really big. And so they could be on the order of gigabytes, if not possibly terabytes of page table. So a number of schemes have been proposed for the size of these huge page tables. So there's hierarchical page tables, and a special case is called clustered page tables. These are ways to hopefully reduce the size of these page tables in the case you have sparse usage. By sparse usage, I mean the entire memory space is not fully utilized. Only parts of it is utilized, maybe 1% or maybe 5% or some small subset of it. And hopefully they're clustered up. And in that case, then you don't need as many table entries as you have entire space. But if you ever need to go to the entire address space, then yeah, you still have that really bad case. And then hopefully clustered page tables could help a little bit. And then there's also hashed page tables. Again, it works well for more sparse usage, but if it's dense usage, it might not be so efficient. Inverted page tables would be one way to solve the problem of these really huge tables. So let's look at some issues here. So if you use a straightforward or what's called one-level page table, what do you have to do? Well, what you need is a way to map a page number to a frame number, right? And then how big your page is. Well, so if it's 4K per page, then that's 2 to the 12 bytes, right? And or 2 to the 12, 2 to the 12 bytes. And because your addresses are assumed to be byte addresses, 32-bit address space or addresses gives you 2 to the 32 bytes. But if you have 2 to the 12 bytes per page, then how many pages do you have? Well, easy. 2 to the 32 divided by 2 to the 12, 32 minus 12, 2 to the 20, right? So the 2 to the 20, which is actually 1 mega entries, right? 2 to the 10 is kilo, 2 to the 20 is mega, 2 to the 30 is giga. So mega is a little over 1 million, right? So 1 million entries, but depending on how many bytes you store in each entry, so let's say 4 bytes, then what do you have then? So 1 mega entries times 4 bytes, that's 4 megabytes. Nowadays, you think 4 megabytes, no big deal, right? Okay, but we're no longer using 32-bit addresses. We're now using much larger. Well, your computer now may have orders of gigabytes, right? And so that would be several thousand times. And then if you keep the same page size, then it wouldn't be just 4 megabyte. It'll be much bigger, right? And how big can it get, right? And so, well, so let's say if you want to use, okay, let's just even stick to 32-bit address space. What you can do is you can do this in 2 levels. So first level would take the higher address bits and then map it to a second level page table. But what's a second page table? Well, second level page or inner, there's outer and inner. The inner page table is one that fits in exactly the size of a page. Okay, so if your page is 4K and then each entry is 4 bytes, then how many entries can each page have? Well, 4K divided by 4, 1K or 1024 entries, right? So an inner page table is, the size of inner page table is defined by the page size, right? And that way, your outer page table just has to map to say, okay, then which page can I find the inner page table? And that inner page table is limited to just that many entries, okay? And then in that case, if it's 1 kilo entries or 1024 entries, then it takes 10 bits, right? So, then within each one, then you have the page offset. Well, page offset is then the remaining bits. So the way this works is outer page table defines the number of bits is really defined by the page size divided by entry size, right? Because the outer page table needs to map the upper bits to an inner table, but inner table is not arbitrary size. Inner table must fit within the page, right? And so then, so 12 is for 4K, and then 10 is for 1K because then the inner page table size is limited, right? So that it's limited to how many entries you can store in a page, right? So we have 4K divided by 4 bytes per entry. We have 1K, so that's why inner page table is 10, and then the page offset, well, that's also 10 because that is within the each within offset within each page, right? So highest order bits would be used to address. Okay, well, it depends on how you do it. So your offset is within the page, right? So I think I should do the offset to that is the remaining bits. Okay, it's okay. This is called forward page table, and so then the logical address. So if you just do one level, it would be just one page table to map the. But if it's two, then what you have to do is further partition the upper and lower bits. The upper bits gets indexed into the outer page table, and then from there you would say which page it is. that contains the inner page table. So that is what lets you find. And then P2 itself is used as the offset within this page of page tables. Then once you find that entry, that gives you the frame number for the actual page, right? So it's done in 2 levels. And if you look at the example above, then outer page table takes you to this, each one, okay, here, like 1 to 500, that is you can think of it as a page. So that's the inner page table. And from the middle bits offset, it then gives you mapping into additional pages, or I should say frames in that case. Okay, so for 64 bits, what happens? Well, you can have many more. So the offset part is the same. Inner page, that's determined by the size of each page, because you have only so many entries within the page. So inner page size, page table must fit in 1 page, right? So all the remaining bits go to the outer one. So that means you have the outer page table still very big, right? So then how big? Well, if you remove 12 bits for the offset within the page, 10 bits for the offset within the inner page table, then you still have 42 bits for the outer page. So 2 to the 42 entries, that's a lot, right? So that's 16 terabytes. If you still assume the 4 bytes per entry, right? So that's huge, because even that itself is likely to be much bigger than your main memory. Your memory is probably 8 gigabytes, 16 gigabytes. This is 16 terabytes just for this outer page table. That's not even counting the inner page tables, okay? So that's a lot. Because, I mean, your hard drive, if you just use an external hard drive, it's probably going to fill up the entire page, even just the outer page table, not even any of the inner ones. So what can you do? You can say, well, let's go to 3 levels. Well, but when you extend to another level, that intermediate level still is limited by the number of entries you can have in a page, right? Because what they index each time is really a page table that fits within the page, that then points to another page table that fits within another page. So if you go in the offset, so because it's 4K, that's 12 bits, but then it's 10K, I should say 1K entries, right? It's that fit in 4K pages. So that's why 10 bits for innermost page table, and then the kind of the intermediate middle page table, that's another 4. And if you have to do another level, you take another 10 bits of the space of the addresses, and then you keep going, and then until one point where you say, okay, that's enough, right? So if you keep doing this, then this would be a 3-level scheme, because you have an innermost page, kind of an intermediate stage and page table, and an outer, or the book calls them second outer page table. Then, well, you know, each of the inner or intermediate would have still, you know, each table size is still your native page size, which is 4K or 1K entries. But outer one still has 2 to the 34 bytes. That's 16 gigabytes. And that's still probably more than your physical memory, right? Yeah.
In this example, we are talking about the second outer page size, the 16 gigabytes. But how about the size of the outer page? Where is going to be stored that outer page?
Right. So that still has to be stored somewhere. Right.
In such a
So-
case, the second outer page and the outer page is gonna be huge. It's gonna be like 16 terabytes.
So
in general, it's gonna be always.
right. So the idea here is you would allocate one, which is the in this case second outer page table, and you allocate the inner ones on demand.
Oh,
Okay. So if you never even touch any of the inner parts, those parts, then you don't even allocate those. And the hope is you never have to allocate. It's doing some lazy evaluation here. But if you really have to use up the entire memory, well, you're gonna be spending all your time or all your memory adding all these intermediate ones because it's not enough to just add another one. You have to add one just to add another inner one, and so forth, right? So that will be a lot of work. And well, for now, even though our address space is 64, logically speaking, in practice, most processors today don't even give you anywhere close to that. Okay, a lot of them limit you to 40 bits of actual address, even though the register stores 64 bits. Some may limit to 48. That's in practice how high these memory spaces really go. Even though logically speaking they have entire 64-bit, but people are just planning ahead. Okay, so this problem in practice hasn't yet happened. I mean, the 64-bit case, we're still dealing about 40 to 48 bit range. Okay, so you don't get an outer page table of 16 gigabyte. You don't do that. But people are already planning ahead, thinking, in that worst case, that's gonna be how big it is, right? Maybe it won't be a problem. Maybe everybody will have exabytes of RAM on their laptop. I don't know by that time, right? But still, at the rate technology is developing, it's hard to imagine that at this point anyway. So, and moreover, it becomes less efficient because it's no longer a single page lookup. You have to look up outer page table or second outer page table just to find the outer page or the intermediate one, and then index it just to look up another one. So you have 4 memory accesses just to get to one physical memory location. Okay, of course your TLB can help with that, but then having to initialize all the data structures, having to link everything, that overheads can be non-trivial. So what do people do? Well, if you ever taken data structures classes, you would know a thing or two about hash tables, right? So what's a hash table, in case you forgot? So hash table is a quick access structure. In Python, you have seen dictionaries, right? Key value pairs. So you give a key as opposed to just a sequential address. And then the idea is that it's relatively sparse. So that is, you're not utilizing most of the entries. If that's the case, by hashing is kind of a randomizing function. So it takes your key and then translates into a number, which is used as the index into your hash table. But that's not necessarily the exact location of your entry, except because you can still hash multiple things to the same hash entry. So in case, that's called collision. If there's a collision, you use a linked list to link those entries that are hashed to the same hash table entry, right? So that's the same idea. So if you know hash tables, you can apply this to your page table as well. And you're betting on the fact that it's not going to be too dense. It still remains sparse. And having 64-bit address space is actually kind of useful, because if it's not using all that, then you just need a much smaller hash table to keep track of the entries. In case of collision, link them using a linked list, right? So this is it's starting to be used more for address spaces larger than 32 bits. And so virtual page number is hashed into a page table, and that's done in the hash structure. And just like a hash table, in case of collision, it has a linked list to the entries. So hashing itself is quick, but then you may have to do linear search in the linked list just to find that entry. Okay, and then what do you have to do? Well, again, take the original key, do key-to-key comparison. If it matches, grab the entry. If not, you keep going until the linked list. Until if it ends, that means it's not in the table. Then you append it to the end, right? And then you update your TLB. If you may need to remap or delete, then you have to go search the linked list. The hope is that you don't get too many collisions, or linked list is not very long, so the access time is still reasonable. But you save a lot in terms of these table entries that otherwise wouldn't be used. Okay, so these entry would contain a virtual page number, that's your key, value of the mapped page frame, that's your value in the key value pair, and as a linked list, you need a pointer to the next, right? Next entry. And so if you understand hash table, that's exactly the way this works, right? You just are using the virtual page number as your key and frame number as your value. So logical address, if TLB matches, fine, go ahead. If not, then do a hash, and hopefully this is much smaller. And then in case of collision, then they are linked in the linked list. And the entry that's matched is used, right? And then you enter that into your TLB. Hopefully you don't have to pay that price over and over again. Now, but for things even larger, especially for 64-bit addresses, people want to use hash tables, but then they figure, well, guess what? The access pattern also changes, because they think it's likely that you would want to allocate a bigger consecutive chunks. And so what they do is they do a variation of these the kind of hashing. So instead of you do a hash from just a page number to find your frame number, you can say, well, I don't want to use so many bits. Instead, I take a few bits fewer, right? Because these are not strings. Unlike Python, you can use a string as a hash key or dictionary key. Here, you're using just a slice of bits, right? And so instead of taking just the upper bits and hash all of them, you take a few less bits, and then the remaining bits are used as offsets into kind of this what's called clustered entry. Okay, so maybe like address, let's just say all with FF something, right? And then instead of using say maybe 16 bits, you use 12 bits. All right, so you only hash the upper 12 bits. What happens to the remaining 4 bits? Well, they would share. So those different addresses will share the same clustered entry. And that clustered entry then will contain the individual mapping. Okay, so each entry is now bigger because it then contains the consecutive addresses, the mapping, right? That way, you do one hash to get not just a single entry, but a table or a short array of entries. Then you use those bits that you didn't hash as offset into that table and look up the entries, right? So this way, it would be much more economical, because then you don't need as many different entries in your hash table, or your hash table, the same number of entries can now handle many more entries, but each entry size now is an array rather than just a single mapping. Okay, and so this can be very useful for memory references that are logically contiguous but physically scattered all over the place. Okay. And so cluster page table is a variation of hash page in that right, so I didn't make a slide, but I think I can just draw it. So previously, if you have an address like, okay, let's say 16 bits that you would use and then remaining bits. The previous one, you would hash that, right? And then, so each one, so like a slightly different bit pattern, like FFCE, right? That's hex, of course. Then it would have its own entry. Hex FFCF, right? That would then be hashed separately, maybe to an entirely different entry. Now, if you use the cluster scheme, then you don't use the last couple bits, right? So you would only hash this many entries here. So instead of 16 bits, you would hash only 12 bits. So that allows your hash table to be much smaller, right? So now you have a much tinier hash table. And so it doesn't matter if FFC or FFCE or FFCF. These used to be hashed to different ones. Now they are hashed to the same one, right? But the entry now is different. The entry size here is just the frame number, frame 1, frame 2. Now here you have another entry, right? And then the last 4 bits, so to the 4, right? And then that's 16 entries here. And then, so you just use offset, E and F, so that's E and F. Okay, E and F, so that's frame 1 and frame 2. Okay, so that way, you can keep the hash table size smaller, or the same hash table size can handle many more entries. Okay, just because now you rely on the last couple bits as offset into an array instead of just a single entry. Okay, so that's clustered. So that means anything that is logically contiguous would then be hashed to a clustered entry. Okay, so that way, now they can still be mapped all over the place, right? To different, right? I mean, they still map exactly the same. So if logically they're together, physically they can be very far away. All right. So that's clustered entry. Though the book doesn't explain this in a lot of explanation, but that's what it means. Okay. Another one is inverted page table. Inverted page table is saying, well, we have a problem of having to create a huge page table, even if you have multi-level or perhaps even hashed, it's still a lot of entries, right? So why don't we do it the other way around? Because your physical memory is fixed, right? If it's fixed, then it really doesn't matter how many processes you have. You don't have to create. If you do inverted page table, then what you're doing is just reverse mapping. You map physical memory of physical address to logical address, right? So then so each entry contains logical address page stored in that physical location and process ID, right? So then that way, when you do so you have the inverted page table. So that means it's a reverse lookup, right? And if it's reverse lookup, well, yeah, actually, hash structure can be very helpful too, because hash structure doesn't really care if you're mapping from physical to logical, logical to physical. It's just key value type of associative lookup, right? And so, but then you then would find, okay, the current mapping, who is the process that owns this page, right? So that way you keep the number of entries the same. So you would have one entry per frame as opposed to one table per process or per page. Okay, so this way it doesn't grow, and then you could still do this kind of checking, just like the case of TLB, which remembers the ID. Remember, right? Because if you do context switch, the process could switch. And here, this also has to remember the process ID. So you would allow access or consider it a match only if also the process ID matches. Right? If not, then it's handled as a page fault. So the advantage is the memory size, because how much physical memory you have, well, that limits your inverted page table. You have just one, and it needs a lot less memory, and it is in use. PowerPC, Spark, Ultra Spark, but then it is actually a problem for the complexity, because if you don't do hashing, then you have to do search. You have to scan all the entries, and it's unclear if you can really do any sorting or binary search, right? So hashing seems like this. But fortunately, TLB helps a lot. So TLB still does the forward mapping, where even though the inverted page table does a reverse mapping, right? But it makes it more difficult to implement shared memory. Why? Because the inverted page table only maps a frame to one process. If you need to handle multiple processes that may share, well, then it becomes more difficult, because then you would need to have possibly an external structure just for bookkeeping, right? And that makes it more difficult. So for performance, hash table is used, and so you can limit the search to a few of these page table entries. And then share memory, what do people do? Well, then you have one mapping virtual to shared physical addresses. So that means unlike the page table case, where different processes may have different logical addresses to the same physical page, here you may have to do some limitation and say, okay, I allow only certain frames to contain shared pages, and they have to be mapped to a fixed logical address. That way you don't have to track different logical addresses in different processes just to share that physical page. Okay, so there are some restrictions, but this seems like one that may be the best solution in terms of really limiting the amount of memory that you have to spend for bookkeeping, and also thanks to the help with of hash tables, you can make the average performance relatively fast. Okay, so Spark, Ultra Spark, originally was done by Sun, right? And Sun got acquired by Oracle, so now it's Oracle Spark, and they do not only the processor but also the OS, and so Spark went to 64-bit pretty early on, and so OS and the hardware, they're tightly integrated, and they do have two hash tables, one for kernel and 1 for all user processes. Okay, and so so what they do is they wouldn't necessarily create 1 for the entire 64-bit address. Instead, it would be 1 where different processes get mapped to the different regions in the even the logical memory. And this way, it doesn't have to keep track of many different hash tables. It's 1, and it just uses different entries as if they were in the same address space, but then because of segment registers and so forth, that way they are isolated. And each entry has base address and the span, which is the number of pages that the entry represents. Okay, so to wrap this up, I'm going to talk a little bit about swapping. Swapping is put in this chapter mainly because of 2 reasons. One is it is related to memory, but then traditionally swapping refers to swapping the entire process from memory to disk. So you can think of it as suspend it, put it in hibernation mode, whichever, and not just put it back in the ready queue, because that's what context switch does, right? Instead, take that image, entire image, write it out to a disk, as if you were saving a file. So disk, well, another word for disk is backing store, because it doesn't have to be disk, it could be flash, it could be other non-volatile storage. So swap out means take the entire process image and then write it out. Swap in means bring that back, okay? And as you can imagine, it's going to be very expensive, right? I mean, even saving to disk, reading file, that already takes some time. And this, and how much do you have to say? Well, maybe program you can just reload, but all the state, right, and all its memory content in use, those at least active pages need to be saved. And so this was done in the old days where you actually, the memory was very expensive, at least disk was more affordable, and so it was worth doing this, just so that you can accommodate many more users, right? Today, the word swapping means something a little bit more specific. So you would swap certain, you might say pages of a process, okay, instead of entire process. So this is called page in, page out. But this is also related to the concept of virtual memory. And so today, even though we talk about physical to logical mapping, the fact that you can do this and then taking a further step by paging to secondary storage or backing store, that's really because of the concept of swapping. Okay, so you can do page in, page out on most modern operating systems, Mac OS, Linux, Windows. But these OSs tend not to do swapping for the entire process. Solaris can still do it in some extreme conditions, but really the modern trend is doing page in, page out. And if you do the top command in most Unix-like systems, they can also tell you or vmstat, you can find out number of page ins, page outs. And so we'll talk about page in, page out in a later chapter. And there's a concept of swapping versus rolling. Okay. Now, when you do swapping, when you want to free up some memory, physical memory, because virtual memory is kind of a way to say, logically speaking, you have that entire address space. But physically, I'm only going to allocate as much as you need, or as little as you need, right? Hoping that you wouldn't have to use up. But then sometimes just wants more. So the OS still has to keep its promise, so it needs to swap certain things out just to free up the physical memory, right? And so what do you swap out? Well, so on Unix you have what's called nice level. You can do man nice, and that's a priority level, and that indicates how many time slices over time you're gonna get, right? Proportionally speaking, and so that way, now if you can do what's called rolling in, rolling out, in the sense that you can dynamically adjust this nice level or priority level, and then as processes run, you change these. You may drop. So those that use up more CPU time, and if you don't fix their priority, they might roll down in their priority level. And after they reach a certain point on demand, they're the first ones that get picked to be swapped out. Okay, so that way it's more like rolling. So now the transfer time tends to be bottleneck, just because there could be an arbitrary amount of memory that that's active, right? And this also needs to integrate with your context switching scheduler and dispatcher, right? Because now it's not just a ready queue for those preempted process. If it's in ready queue, it could actually be swapped out, right? And then so that the status needs to be indicated accordingly. So it needs to be brought back to memory before it could be put back in ready queue again, right? So swap in, swap out. Yeah, that's really that simple view of it. And for mobile systems, well, because nowadays we have a lot more RAM, and also this is flash memory based. You do things a little differently because, for one, the flash is, you can say it's, even though it's backing store non-volatile memory, it is still kind of memory, right? And certain systems can do what's called execute in place. So they can view flash as an extension of their memory space. So ARM processors can do this with their built-in flash. External storage flash, you may be able to do certain mapping. So in that case, there's really a lot less need for copying from disk to memory. It may be able to just run directly out of some parts of flash memory, right? And also you want to avoid doing a lot of rewrites on flash. Why? Flash has limited rewrite cycles. NAND flash may be on the order of say 100,000 cycles. And so if you do swapping or even paging, you could actually wear out flash. So try this on, say, something like a Raspberry Pi, or something that you can, a little single board computer you can boot up on an SD card, okay? And you put Linux on there, or you put some Android ports, and go into a place where you configure to enable swap, which it may be already enabled, and run it. After a few weeks, you'll kill the flash, okay? So on mobile devices, you really got to be very careful. So you do want to disable swapping, and instead you want to manage the memory differently. So mobile OSs like iOS can have additional kind of signal or notification to the process and say, here, free up some memory. If not, I'm gonna grab it from you, but I'm being nice to you. So here's a heads up, right? And in fact, it would even throw out, it knows what's read-only. So code could be read-only. Maybe certain data tables could be read-only, right? And it knows certain parts it can do on its own without having to tell the process. And these tend to be flash-based, so you might not even need to save anything. And the process better cooperate. If not, then OS would then say, I'm going to kill you, right? Android may do some saving or terminate an app if it's running low on memory. Okay, but it can save the application state. So that is in a way like a swap out and swap in. Okay, and that way, and also modern OSs do some kind of saving of processes for another reason. Not necessarily to free up memory, but like if you want to reboot and then be up and running again with the same programs, that's a lot like hibernation, right? So some like Windows has this hibernation mode. So if you leave your laptop unplugged and battery is running out, what it does is then it dumps the memory to disk, and then next time you open up, it actually may be in say, okay, well, I'm trying to reconstruct it, the memory by reading from the images saved to disk, right? So swapping could be used for that purpose. Hopefully you wouldn't have to restart everything, but it could work in certain cases, might not work. So for example, your network connection wouldn't work this way because you may save all the connection state, but then after you put it in hibernation state, you'd lose the connection. You have to reestablish anyway. So by restoring like the network state, that's not going to help. It's disconnected anyway, right? But for a lot of other computation type of state, then yes, you wouldn't have to reload those. You just directly can reconstruct the memory content. Okay. Okay, so that is what I have for this chapter, and I do want to point out that now that midterm is over, please work on your project checkpoint. And it's important. It's a big part of your grade, and as you saw on the midterm, I do ask some questions, a few questions just to see, but even if I don't ask midterm or final questions, still I think it's important that you understand the concepts. And on the midterm, I just want to show quickly, do we have midterm? This is a histogram in case, do we post this? No, okay, so highest score was 29 out of 30, so, and yeah, so now you get an idea of multiple choice. You got to read your questions very carefully, and so as you know, I don't just take question one-to-one from the review, weekly review. I would take, because those are very simple questions, right? But you got to do those, and you got to know those. And what I do is I combine maybe 4 or 5 of those very simple questions into one multiple choice. So that's my style. I'll continue doing this, and expect the final to also cover some of the same materials, maybe even similar questions, just slightly rephrased. And
The final exam
yeah,
is going to be
everything. Yeah, final will cover everything.
Will it be the same style?
Yeah, most likely, yes. Yeah. Don't give up yet. don't just because you haven't gotten a score as high as you expected. Don't give up, because there are still a lot of opportunities for you to bring up your grade. This is more of an intermediate feedback. And if you have questions about your exam, do make an appointment to see a TA. You are allowed to go over the graded exam, but we don't let you take out that. You can look at the exam and then possibly even bring the review questions and then take notes on your review questions, right? Or ask TAs. Yeah, I mean, this is really a feedback for you to see, did you really understand the material, not just superficially, but with a little bit of depth, okay?